Well, thank you, Dr. Fisher, for the introduction. So as she said, I'll be presenting my work on SHAKER, simulation and harmonic analysis of case-based readout. This is some fMRI simulation software that I've developed under the direction of Dr. Daniel Rowe over the past year and some change. So to start, we'll go over some background of MRI, which I'll probably just briefly go through that looking at the crowd. I think most everyone here has at least some familiarity with that. So we'll go quickly through that. I'll go through a description of the software we've built, and then I'll do a quick demonstration to show how it might be used. Okay. So MRI, magnetic resonance imaging, it's a non-invasive medical imaging modality. In our case, it's most often associated with the human brain, but it can really be used for any soft tissue, so organs, muscles, tendons, things like that. The MRI machine uses a combination of very strong magnetic fields, something like 20,000, 60,000 times stronger than the Earth's own magnetic field, as well as strategically timed radio frequency bursts to collect this complex valued data that is then later reconstructed into an image. So every image from an MRI machine comes from a pulse sequence. This is the most basic element. This is kind of what determines the signal you get from the machine. So the most common one, especially in fMRI, is this gradient echo pulse sequence, which I have a simplified version of over here. So just looking at a few of the pieces here, this RF line, this is the radio frequency pulse. So every image starts with a radio frequency pulse. This GSS is your slice select gradient. So that's choosing which like Z level of brain or tissue you want to image. These next two, this GPE and FE, these are your phase encode and frequency encode. These are how you navigate what I'll call K-space, and we'll look at later. It's the space in which data is collected in fMRI. So this is just pushing an imaginary point in this space where data is sampled. The signal, that's what we're measuring. And then two important time parameters I want to mention are echo time. So that's the time from your radio frequency burst to your peak signal, and repetition time, which is the time from one radio frequency pulse to the next one. Another way to think about TR, or repetition time, that's the time between two successive reconstructed images. So if you want to reconstruct images really quickly, you need a really small TR, which there are some physical and biological limitations to that. So the signal in MR generally comes from two relaxivities. So the way it kind of works is you have this net magnetization of hydrogen nuclei in your soft tissue. So the strong magnetic field aligns, a large portion of these hydrogen nuclei's magnetic moments in the longitudinal direction along the length of the machine. This RF pulse tips that net magnetization at some flip angle. 90 degrees is common for fMRI. And then two relaxivities occur. The first, they occur simultaneously, but the first I'm going to list is T1 relaxation, or longitudinal. So that's this relaxation from this transverse plane XY back into the longitudinal direction. So this net magnetization tilting back to be aligned with the main magnetic field. And then this T2 star relaxation, which is a dephasing of these hydrogen nuclei magnetic moments. So initially they're all spinning in phase after this initial tip, and then they start to dephase in the transverse plane over time. This one is of particular interest, fMRI. We're looking at a T2 star effect, the bold response that comes from blood oxygenation. So this one is, for our purposes, maybe more interesting, but both are incorporated in our later work. So the MR signal is collected from the signal equation, which I kind of skip a decently important step here, which is the block equations. So this is a system of differential equations that govern the physics operating behind the machine. And these change based on your pulse sequence settings. So, if you're using a gradient echo or perhaps like inversion recovery or spin echo pulse sequence, you're going to get a different set of block equations to which you can get a solution, which is called the signal equation. So here I have the gradient echo signal equation, which I want to just list a few of the important parts of it. So in red, I've got this M0, T1, T2 star, and this gamma. So the M0, that's the net magnetization, T1, T2 star, those are those relaxivities I previously mentioned. And gamma is just a gyromagnetic ratio. It determines the speed at which these hydrogen nuclei magnetic moments precess. So the things in red are inherent to the biological tissue. So those are things you cannot change. Like white matter, gray matter, they have a T1, T2 star value. As a technician, you can't change that. It's just what it is. The things in blue, however, are things that a technician does have some control over. So that would be the flip angle. They can specify the angle they want that magnetic moment to flip, the repetition and echo time, and then this last one is a little more hand wavy, but that's just time at which each K-space location is sampled. So there's some FDA limits in terms of how fast you can sample or move across K-space. So there's some limits to it, but to an extent, a technician can somewhat control the time at which K-space locations are sampled. So conventionally, here we have a K-space array. Conventionally, most commonly, K-space is sampled in Cartesian rows. So you'll start in the center, you'll go out to a corner, scan a row, do some turnaround, scan a row, keep working your way down. Often in this scheme, there will be 3 to 5 rows in the middle that are sampled twice, just for some Nyquist ghosting corrections. Um, the reason this one's so popular, it's simple to understand, it's simple to implement, and it's very easy to reconstruct images. When I get to it later on, the reconstruction of images for Cartesian K-space is just inverse discrete Fourier transform, and you're done. But you can do whatever path you want in K-space as long as it follows a continuous path. So on the right, I have a radial trajectory. So you can imagine doing a spoke across K-space and then turning around, doing another spoke across, turning around, doing another spoke, so on. So you can play all sorts of games here. You can do spiral, you can do whatever you want, as long as you're covering K-space. And there's different advantages and disadvantages for all the different coverages. Cartesian is just the most common one because it's simple and it works well. So at each K-space array element, you have a spatial frequency that's complex valued. So a real and imaginary part. This is the data that's coming directly from the machine. So the raw data is complex valued. So real and imaginary. An alternative way to think about that is magnitude and phase, especially in image space. Magnitude and phase is generally all we really care about, in particular the magnitude. So it's important to think about the raw data that we will be simulating will be complex valued. So it's interesting then to look about this data we'll be simulating, this K-space data. What are the distribution of these K-space elements? So if you look at a single K-space location throughout a time series, so look at that same K-space element at different images throughout an fMRI experiment, it's well understood that the real and imaginary parts of that K-space element would be independent and identically normally distributed with phase-coupled means. So here you can see that joint distribution where this first part is the real normal distribution and the second part is the imaginary normal distribution. Easily separable, marginal distributions would just be normal as well. If we want to look at the magnitude and phase scheme, however, we can just do a transformation of variables, which I've listed here. And when you do that, you get this joint distribution for the magnitude and phase. And if we want to separate that out into our marginal distributions, we just integrate out the opposite parameter, respectively. And we end up with a Ricean distribution for the magnitude and this unnamed non-normal distribution for the phase. So what does that look like in K-space? Well, it kind of depends where in K-space you are. If you're towards the outer edges of K-space, so here, this top row, where the signal or true magnitude is low, this Ricean distribution for the magnitude becomes Rayleigh. It looks like a normal distribution with like a long right tail. And this unnamed non-normal distribution for the phase becomes uniform. So you just have uniform noise from minus pi to pi for the phase. When the signal is high, or the true magnitude is much greater than 0, so near the center of K-space, this Ricean distribution for the magnitude becomes normal, and this unnamed non-normal distribution for the phase does become normal, centered around the true phase of that K-space spatial frequency. The same thing is true for image space, because the Fourier transform of a normal distribution is still a normal distribution, so these would hold for image space as well. But because we're simulating in K-space, we really just care about K-space. Okay, so as far as reconstructing image goes, like I said, for Cartesian K-space, it's very simple. It's just inverse discrete Fourier transform. Very simple. MATLAB has a function for it. I'm sure Python, R, all probably have some function or easy package for it. Um, if you do a more interesting trajectory of K-space, like the radial one, at that point you'll usually have to have some sort of algorithm, regridding, approximation, something of that nature to either get it in a Cartesian grid or do some sort of approximation to get an image. There's been a lot of work done on that. One of my later projects will actually be involved with that as well. But it's just an extra set of steps you'll have to take to reconstruct an image. On the right, this is a figure I took from one of Dr. Rowe's chapters in Handbook from 2016. This is just a matrix depiction of how the reconstruction is happening. We don't do this in practice. This is just a good way to visualize it. Where here you have your K-space array in the second column, and you pre and post multiply it by the inverse Fourier transform matrix, and you get what we'll say the four parts of a reconstructed image are. You have the real and imaginary, and then you have the magnitude and phase. And maybe looking at these, it's maybe natural to see why people generally only care about the magnitude. If you're looking for any sort of biological detail, this is generally the one to look at. However, the phase is still important data. It's half of the data you're collecting from the machine. So to discard it or ignore it could potentially mean missing out on important biological detail or information, especially when we're talking about the bold response, which is a T2 star effect, which has an effect on the phase. Another more popular thing, especially in fMRI recently, especially when we're thinking about rapidly accelerating the rate at which we collect images, would be parallel imaging. So conventionally, there's just one coil in the machine collecting one image at every TR. But what can be done is you can use multiple coils. So here I just have a simple 4, but it could be 4, 8, 16, 32, however many they want to fit. Where at each TR, instead of getting one image, you get 4, in this case, coil sensitivity weighted images. And I have that on the right here, what that would look like. So you can see, this coil would be towards the front of the head and it'd be more sensitive to that area. The benefit this gets you is if you're trying to speed up fMRI, you can subsample your K-space and use something like Sense or Grappa to really accelerate the rate at which you get images, which is an incredibly desirable thing to do for fMRI. So in fMRI, it's all of what I just talked about, except we do a ton of images in a row where you do blocks of non-task, so the patient just, lying there passively, and task active blocks. So one we're particularly interested in, or the canonical example, is just right hand finger tapping. So if you tap your right fingers, you expect activation in your left motor cortex, which is roughly what I have visualized here. And this is a result of the blood oxygen level dependent response, or the BOLD signal. So the BOLD signal is a correlate for neuronal activity. You tap your right finger, your left motor cortex, there's neurons firing to activate that motor action, and the blood flows there as a result. And that can be measured using fMRI. So the point is to capture this BOLD signal and then map it to a certain region of the brain that we expect that task activation to be important to. Something important to note, this BOLD signal, it can occur over 3 to 4 seconds. The average, standard fMRI rate for an image is 1 second per image. So you can imagine getting images at a much faster rate is really desirable. If you have this signal change over 3 to 4 seconds and you're only getting an image every 1 second, you're trying to capture a whole signal change in potentially 4 images, which could be really difficult to do. So accelerated imaging, things like Sense and Grappa, are really desirable to try and get, maybe an image every quarter of a second or so. Okay, now I'm going to move on to SHAKER. I'm going to talk about how I take all of what we just talked about and put it into our software package. So the challenge that a lot of statisticians in fMRI might face is that data can be expensive to obtain. It can also be just difficult to obtain. You might not be able to obtain raw data. You might not even get all of the data. Some statisticians might just get magnitude images and that's it. No K-space, no phase, just a part of the data. So the solution to this is to test your developing models on simulated data. It's not unique to fMRI. That's a very popular thing, of course. You simulate data, you test your model, you develop it there, you get some experimental data, and then you test your model or validate your model on that, and then hopefully everything checks out. Um, the challenge that comes with simulated data is that, especially for fMRI, it's often created in-house, so a lot of different people are doing a lot of different things, and it might not accurately reflect the data that truly comes off a machine. So one package that we looked at a lot when we were developing our own was this NeuroSim paper, and they created a simulator that was very useful. It got many citations. A lot of people produce a lot of good work from it. And we looked at it and we thought, how could we improve this? And one of the biggest improvements was adding phase. A lot of simulators out there don't include phase, or they just operate directly in image space, not in K space. So our solution is to create a physics-based fMRI simulation software tool that has accurate noise modeling and just modeling of the simulated data. So we're going to be simulating in K space, magnitude, and phase using the signal equations that are well understood from the physicists and biologists who have worked on fMRI. So this is where we introduce SHAKER. This is our tool. So it's a physics-based tool, as I've said. It's built on the MATLAB framework. Fortunately, you don't need to know MATLAB how to use it. You just need a MATLAB license because it's entirely GUI-based. If you have MATLAB knowledge, that's going to help because there's some inputs you can do of your own if you want. Nothing required, though. Everything's preloaded. So it's a standalone. You could just download it right now, simulate data, and be done with nothing else. All of the settings you can change. You can save a state of settings and then tag it with like some simulated data, send it to somebody. So if you simulate data with these settings, at a later date you can simulate it with the exact same settings, which is good just for reproducibility of results. Anytime you simulate data, there's a simulation summary provided, which is nice. It's just like a short blurb of text you can copy paste, put it in a notepad or something just to like remind yourself of how you simulated that data, or put it in a paper, or whatever you're doing with it. So I'll go through each of the panels of SHAKER pretty quickly so I can get to the demonstration, and then show you guys kind of how it works. So in the top left, this is where you can see the digital phantom that's built into SHAKER. So it's simulated with values from a 3 Tesla machine. It has all the maps I talked about previously, so that would be your net magnetization, T1, T2 star, and your delta B, so that magnetic field inhomogeneity. There's an activation map built in also. That one lives separately from the Phantom, and that's just for like right-hand finger tapping. You can adjust all the MRI parameters. So these are all things that, like an MRI technician might be able to change at the machine. So that would be like the signal equation, the trajectory, so Cartesian is most common, the acceleration factor, simulated field strength, echo repetition time, flip angle, effective echo spacing. You can do an increased number of coils. The way SHAKER has it is they're radially symmetric, but you could upload your own coil files if you want to do it in a different way for whatever reason. Reconstruction method. And then what you can also change, because it's simulation, why not? We can do what we want. You can change these biological values that are inherent to the tissues. So, this net magnetization of the white matter, gray matter, CSF, T1, T2 star, you can change all those if you want. They'll change in the Phantom and simulate properly. So here you can generate a single K-space array just to look and make sure everything's simulated, at least for one TR, how you would expect before you move on to simulate a whole time series. The next tab there is the task design. So here's where you can specify what your design looks like. So, some initial rest images before you have however many epochs with N task images and M rest images that repeat. You can specify the SNR of your simulated data, and then you can choose the CNR of your activated data or your activation region. And you can also include some phase in the activation if you want. And then here's where you would simulate your whole experiment, which would then bring you to the top right, which is where you can kind of just do an exploratory analysis of your simulated data. So it's really just to look and make sure, your simulation went as expected. You can leaf through all the time points. You can look at activated slices. You can look at individual voxel time series just to make sure that, things went how you expected. And if you're looking in image space, things were reconstructed how you would expect them to reconstruct. And then this is also where, if you want, you can be done with Shaker here and export your time series. That'll export your k-space array, or your time series of k-space arrays. Alternatively, Shaker has some built-in statistical analysis tools and support for your own statistical analysis. So here you can choose what kind of statistic you want to look at, with some options there, or you can look at the voxel histogram. So here in this example one, you can see this Rayleigh distribution, or this Rayleigh distribution rather. So this is probably the magnitude of some voxel out in space. Okay, so I'll change my stream now so I can hopefully show you Shaker in use.
This is very cool, John.
Thank you. All right, is that live?
Yes.
Awesome. Okay, so this is what Shaker looks like. So here you've got your phantom. You can look at all the different maps if you want. It's a full 3D phantom. So, if you want to do sagittal coronal slices, that's totally fine. I'm just going to stick with axial. You can leaf through that. If you want, you could import, a different phantom, a different file. So let's say I want to do a different activation file. Here I have a different one. So I've just imported it and I can overlay, see where it looks like. So this activation file is going to give me activation here. So we can just leave that. Down here, I can change all the parameters I was talking about. So for signal equation, I'll leave it gradient echo, but you can see all the other ones. You're also going to see this template pop up a few times in some of these dropdowns. So I've built a template for many of them. So if you want to implement your own signal equation or trajectory or reconstruction method, there's a template here. So if you have something already, you just need to reformat it so that it takes the inputs and outputs that Shaker expects, and it'll just work right away. So we'll leave that gradient echo. Trajectory, same deal. There's a template. So if you have your own trajectory, like spiral or something, just follow the template, plop it in, and it'll work. We'll stay with Cartesian. Acceleration factor, field strength, echo time, repetition time, flip angle, SNR, we can bump that up. Maybe 15 is more reasonable or something. All things you could change. Here, this table of values, you could change that however you want. These are the simulated values for a 3 Tesla machine, but if you have like a 7 Tesla or like 11.4 that you might be experimenting with, these values might change a little bit, so it might be convenient to change those. You can bump up the number of coils if you want. And then here's where reconstruction, you can change that. So there's a template for that. So it's not included yet. It's something I want to do, just haven't got to. Like a base sense or grappa reconstruction, you could just plop a file in here and it would reconstruct totally fine if you had, some acceleration factor. So we can generate a single k-space. And that'll take just a second, hopefully. Yep. So there's our simulated k-space. So we can see its magnitude, we can see its phase. Because we had the reconstruction, we can also look at its image space, magnitude, phase. If you want, you can also look at the activated slice. In this case, not much is going to change because the CNR I have on another tab is pretty low. So you don't see anything, but just in case you want to mess with it, you could. So at this point, it looks good. Let's go to the task design to try and get our fMRI experiment set up. So here the HRF, or hemodynamic response function I have, is just a block function. Future versions, I'd like to add support for convolutions. Gamma or double gamma I've seen are pretty popular, so I think that would be a pretty interesting tool to add. But here we'll say we have 10 initial rest images followed by 20 epochs of 15 tasks and 15 rest images each, which if we plot that, not terribly interesting, but you get what you expect of a block design. This task, we'll say, has a CNR 0.75, and we'll not bother adding any phase activation for now. So we're ready to simulate. Yep.
Yeah, sorry. So you could have multiple tasks. Could you define multiple regions based on the initial activation overlay where you expect like responses from task 1 versus task 2?
So task 2, this is oops.
Okay, cool.
It's to
awesome.
come. Yeah. Yeah, I maybe should erase that tab, but I left it just because it's something on the back of my mind that I want to add.
No, absolutely. Okay, sorry.
No, that's great. That's a good thing to remind me about. So that there was our simulation that happened in that little bit. Here you can see the simulation summary. So it just gives some bits about time, date. It lists all the settings I chose, things like that. So you can just copy paste that in a notepad. So if you're worried about like how did I simulate this data, there you go. So we can look at these images, leaf through them. You're not going to see too much interesting stuff. Um, if you want, you can look at a certain voxel's time series. So, this is an unactivated time or unactivated voxel. So, really just noise throughout time, what we would expect. Um, if we want, then we can try some statistics. So maybe we want to do a t-test on the magnitude of image space. And if we do that, hopefully we'll see some task activation right where we expected it. We can mask the empty space to ignore the space, or we can superimpose on the anatomical just to see where that lies, like biologically. Another interesting thing, let's do this same voxel. We can look at the voxel histogram. So that just shows us the sampled voxels or sample data from this voxel throughout time, and it follows that theoretical, what would that be? That would be a Rayleigh distribution because it's a magnitude of an interior voxel. And so what you can do with SHAKER is you can export your time series here. So if I click that, you can save it, do whatever you want with it. You could also export your set of MRI parameters, which maybe I'll import a set of MRI parameters to see what that looks like. So here's some work I actually used SHAKER for. And if I import that, you'll see some of these numbers changed. So it changed my phantom size to 128, my slice to 83, changed my echo time, my effective echo spacing. So you can imagine, if you have a set of settings on SHAKER that you like, that you feel like you simulated good data with, save it, use it again some other time. And then lastly, just this empty space. That's just for future development. There's an RNG seed, so if you want to seed the same noise every time, you can do that too, just for reproducibility of results.
Hey, John, I have another question. When
Mhm.
you're exporting your time series, you're not exporting them as a Nifty file?
It says a .mat. So
This
this,
is a .mat. Okay.
yeah, I think R would be able to, I'm sure there's an R package to
Oh,
interpret,
yeah, I think there is.
or Python or
Yeah.
anything like
Yeah,
that. But yeah, this would be just a MATLAB file.
yeah, it's r.matlab. That's the
Okay.
package.
Okay.
Yeah, so I
Okay, great.
imagine I don't use R myself, but I imagine that's probably not too difficult to use.
No, that's fine. Okay. Awesome.
Hmm. Right. And then I'll go back for the last couple slides.
So um, how do these simulations compare with NeuroSim?
They look comparable. It's a little bit different because NeuroSim simulates an image space and they do magnitude images,
Yeah, that's right. Yeah,
and whereas we're simulating in K space and doing complex and or magnitude and phase. So you're getting a little bit more here in that regard. NeuroSim
sure.
does
Yeah.
have a sorry.
No, no, sure, of course. Yeah, yeah. But my question is really, how do these magnitude images compare with NeuroSims? Have you looked at that?
I mean, visually, I think they look comparable.
Okay.
Um,
Because if you read NeuroSims, that paper, they seem to say that they've done a lot of stuff, and it's not completely clear to me, at least, what they've done. But I mean, there's a lot of. I mean, if you read that paper, their paper, that is, this is like about 12 years old or something, right?
mhm.
And so how they do the noise characteristics is not completely clear. I mean, it is normal, that part is clear, but I don't completely understand how they do the noise characteristics there. So that's why I was wondering. Well, so yours is very simple noise, right? Like simple in the sense that it is Gaussian noise with independent, um, uh, basically, basically what leads into Rice noise, right?
Yes, yeah. Gaussian in the real and imaginary, and then you get that rice in the magnitude.
Yeah, yeah. And but do you do any spatial noise, like
Uh,
spatial relationships?
not right now, no.
Okay, okay, fine. Yeah, I see. Okay, sure.
But John has talked about adding support for processing, so that way you could look at what the effects were of the processing, and hence, induce the local correlation from processing.
Mm. Yeah, I'm not a great fan of NeuroSim, frankly, though, because I've actually used it quite a bit because I was asked to use it by a reviewer, and I noticed that if you actually increase the SNR at one time, at some time, it switches. The performance of methods actually switches, which I think is not a problem of the method. I think it's the simulation, but I don't know for sure. So anyway, but that's the same.
Yep. But that leads me well into what I was going to talk about next, which is my future work for Shaker. So there's, I think it's at a good place now. I'm using it to simulate data for another project I'm working on. However, I do think there's, of course, always more to be added to it. So I think there's some interesting MRI parameters that I could add. So field of view, bandwidth, one I'm working on adding right now. You can see it here. It's not functional yet, but it involves including those first three images of an fMRI time series that are generally brighter than the rest of an fMRI time series. So I think that, especially for projects I'm working on, that would be a really important feature to add. I think it would be good to add SMS methods. So simulating multiple slices scanned at the same time in Alias. One of my colleagues, Ke, works on that. So I think it would be really helpful for people working on SMS techniques to have something like that. I want to add inter and intra image motion. So, patients aren't perfectly still in the machine. I want to simulate some sort of like wobbling either within one image or from image to image. I think that would be really important for anyone trying to do like spatial modeling of that. And then just built-in reconstruction and statistical analysis techniques. So right now, I just have the basics, the bare basics. I think it would be really good though to up that, at least include things like sense, grappa, CNR measures, things like that, and statistics. And then one bullet I'm missing here, but thankfully Dr. O mentioned, is the processing of images. So there's many things that can be done to the data before or during getting to an image. Things like apodization, um, zero filling of case space, smoothing, things like that. I want to add kind of a a space on Shaker for people to implement those sort of things. All right. Lastly, I just want to acknowledge some people that have helped me with this project. So Dr. Rowe, he's been advising me my whole time at Marquette, especially on this project. Chase Sakaitis, he just graduated last year. He was very helpful. He taught me a lot of what I know about fMRI. And then lastly, Koju, who's actually defending her dissertation in, I don't know, 12 days or so from now. So thank you to those three people in particular. Thank you all for attending today. If you have any questions, I'd be happy to field them.